Okay, so let's get the party started. So the foundation at the core of math is proof. So in calculus, you sort of once in a while we give you a sort of elementary proof, or we might sketch an argument. Those of you who had me, you might remember doing certain things like prove why this function has exactly one root, or verify this, and you have to have this line of reasoning that has no logical flaws. That's really at the heart of mathematics, and you might think, well, why? Who cares? Well, there's lots of reasons we care. Maybe human curiosity. We want to be precise. We want to be absolute now. We want to be absolute 1,000 years from now, and we wanted to be absolute 1,000 years before now. But also, it's because mathematics is in many ways the language of nature. Those of you who have ever really thought about calculus and physics, you'll see that is in fact the case. And so, and there's many other examples I could give you of where mathematics plays a very practical role. In fact, it plays an extremely important role in the world we live in. How do we explain and model and do things? And when we use theory from mathematics, that's different from theory in, say, physics or chemistry. If you look at physical theory, at one point we thought the sun was not the center of the universe. We thought it was the earth, and then we've proven that theory wrong. But in mathematics, the Pythagorean theorem has always been true. It's never going to be false, ever, ever. In biology, we have different theories. How do we cure this? How do we cure that? Years ago, if you were sick, they might cut you and let you bleed and say we're going to bleed the demon out and you'll be healthy. We don't do that anymore. If you were crazy, they might do something like put a hole in your head and say that we're going to let out the insanity out of you. Google the term hysteria and where that comes from, and think about how they did certain medical things. So in many branches of science, things change. And they change often. Theories change. Our theory of an atom has changed over the years. It will likely change again. Newton's theories are true for many things, but they don't hold for everything. We had to invent new theory, quantum physics, relativity. Mathematics, it's the theory we speak of is in absolutes. It's not in we think this to be true because we observe it in certain situations. It's because we can logically show that it's always true. And the way we do that is we do that with proofs. And it turns out that computer science is in very much the same circle that without mathematical proof and logic and rigor, the science itself doesn't exist. Programming doesn't exist. So in many ways, this is a great course for computer science students to take, and also for us to teach math students. So what we want to do now is give you a brief overview, not overview, we want to give you an introduction, I should say, to how we do this. So what a proof relies on is what we call is propositional logic. So that's going to be our topic today. And what we want to do is we want to get you thinking in these ways. If you looked at the first homework assignment, you might think this doesn't even sound like a math class. And that's because, as I said before, the math you've seen is only such a small bit of what mathematics is. And it's mostly computational stuff, procedural stuff that you've learned. Yeah. 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 You guys got to check Canvas out all the time. It should be like every morning. No. And also set your, what I would do is go into the settings of Canvas and make sure that if you have, it sends you an email anytime I update the site. I mean, again, that's, you know, especially now that we're like meeting half and half, all that crap, you really got to check out Canvas. I think the homework's due Monday night, right? So that'll give you a chance to, we'll do examples like that today. That'll give you a chance to ask questions Tuesday if you have any. Give you a chance to have questions on email, all that stuff. So look, one of the things that I can't emphasize enough in a class like this is you got to read the book. I mean, think about a course. The way a university level course works is you're responsible for what's in that book. We can't possibly go line through line with what's in a book. So you have to read it and then read it again, and then you have to ask questions. And you have to understand that every possible type of question you might be asked, we can't do every single type of example in class. There's just not enough time. We will give you the important things. We will give you as many examples as we can, but the learning has to start and end with you. I am only a resource. So, what we're going to do, and the way mathematics works really is we try to think of it as a hierarchy. And you see this a little bit in calculus, but we make a set of definitions. We make a set of things called axioms that we all agree upon. We say this is true. Maybe these axioms are obvious. Like, you know, maybe we say, okay, we all agree that numbers are commutative when you add them. 4 and 5 is the same as 5 and 4. We all agree in that, right? So we might say that's an axiom. But we might also have axioms that we don't really have intuition for, but we do find out they're useful. So once we make definitions and we make axioms, what we do is then we try to deduce things from them. We call these things propositions, or we call them theorems, or we call them lemmas. And you may have seen these words before in a math book. And the way we derive them is through this logical reasoning that we call proof. And these proofs are going to start with this, what we call propositional logic. So what we got to do is we got to start from the beginning. So a statement or proposition. So it depends on where you read some of this stuff, depending on what resources you use. Our text, I believe, uses the word proposition. Is a sentence that is true or false. So it can't be both. So that's a very important sort of thing to illustrate. So if we give an example of one, so you might say something like in English, Pittsburgh is in Pennsylvania. I guess we should spell it out. That is a sentence. We can either verify it to be true or false, correct? One plus 5 equals 6. That is a sentence. It happens to be a true sentence. We can verify that, right? If we agree on arithmetic. 1 plus 4 equals 10 is a proposition or a statement. It's a false one. We know 1 plus 4 isn't 10, although we can get into that argument if we want it. But let's look at non-examples. I keep hitting the wrong mouse. This is funny. So Pittsburgh is fun. Well, you can't declare once and for all that that's always true or always false, right? You might say that's an opinionated thing. That's an example. And then if we do a little math in it, x plus 5 equals 10. Well, we can't say whether that's true or false because we don't know what x is. All right, does anybody have a question about that? So what we'd like to do, yeah, what's up, Michelle?
So for our homework, like, let's just do the first one. So how would we write an answer for that? Like, Pittsburgh is in Pennsylvania. Do we just write true then?
Well, I mean, oh, but I'm not asking you anything. There's no question here. Okay. No, that's okay. You know, that's fine. You say it that way. Look, I'm not asking you to do anything. I'm giving you 3 examples of a statement, and I'm giving you 2 examples that aren't statements. That's all. I don't care whether they're true or false right now. What you need to understand is these ones can be verified to be true or false. These 2 cannot. Does that make sense? You can't verify. What context can we verify that Pittsburgh is fun? It's not declarative. And we can't verify that this is true. We can't verify that x plus 5 is equal to 10 because we don't know what x is. But I can verify the other 3. Does that make sense? Now, of course, you could say that's true or false. Now, on the homework, I didn't ask you that. On the homework, I asked you to negate something, but we didn't talk about that yet. Does that make sense?
Yeah.
No, it's all right. This is going to get even more confusing. Don't worry. That's what happens. So we want to study generic statements. Just like in math class, in calculus, we study arbitrary functions. Sometimes we give you a rule. Sometimes we just say let f be continuous, or we say let f be differentiable. In algebra class, when we're studying the relationships between numbers, we often use variables, right? So we do the same thing with generic statements. So it's convenient to denote an arbitrary or generic if I could spell, it would be lovely. Generic even a good word to use now? That's kind of, let's just use, I mean, you could think of it as generic, but let's just say an arbitrary proposition or statement. So since it's arbitrary, just like in algebra, we use the word variable. So now you have 2 contexts in your life for variable. A variable can be an unknown number like x, y, or z, but it can also be an unknown statement or a generic statement like p or q. So it's typical to see p, q, etc. I shouldn't say etc., but maybe let's use these guys. So its truth value conveniently enough is denoted T or F. So if you want to put a truth value to your previous example, as maybe, Michelle, you pointed out, the first one is true, the second one is true, and the third one is false. Does that make sense? Okay. So you might even see where this is heading. If we have, for example, a mathematical statement, we might want to know, is it true or false? And then we might want to know, when is it true? When is it false? Could be sort of like a conditional thing. So what I mean by that is, if you go back, this sentence alone can't be verified true or false. This sentence alone can't be verified true or false. But if you sort of modify them and put them in the correct context, that you could rephrase a statement so that it could be verified true or false. And in other times, we might want to verify this. This might be false if we think about 1 and 4 in the traditional sense. But perhaps we want to think about 1 and 4. Maybe we talk about, and this might be a little over your heads, we mentioned this on Monday about the idea of using different number systems, where that could be true. So what I'm saying is these statements, the first 3 alone can be verified true or false, but we might also want to add something to them, join them with other statements. We want to build new statements from old statements. Right? And you saw this already in math classes. In calculus, we'd say, okay, if this is true, and if this is true, then this is true. Or sometimes we just said, if one thing is true, then something holds. Because you could adjust that. Look at the very last non-example. You could say, okay, if x is 5, then this statement is true. If x is any other number, it's false. So what we want to do is we want to take statements and be able to combine them and make more compound statements. We want to be able to work with them. Just like when you first started with algebraic expressions, you learned that you can add, subtract, multiply and divide. Well, we can't really add an English sentence to another English sentence using traditional arithmetic, but we can combine sentences. And we want to start being able to do that. Does that make sense, maybe? All right. Any questions, by the way? All right, good. So, let's change our color. So it's useful to operate on statements, just like we operate on numbers. By the way, don't forget, anytime I use the word statement, a synonym is a proposition. So we need to define operations. Does that make sense? Just like when you were a kid, you defined addition, subtraction, multiplication. You defined exponents. You defined operations. Then you defined them on algebraic expressions and functions and all that. Now we're much more generic now. We're just saying, here's a sentence. How do we operate on it? So let's do that. The negation of P, and this is an important concept, and it is denoted one of 2 ways typically. It's denoted with this sort of upside down L or a squiggly in front of P. This means not P. So think about it in an intuitive English colloquial sense. If I have a statement and I want to negate it, just think of the English definition of negate. It's the opposite, right? And so that's exactly what we want to say here. Now, in terms of truth value, the opposite of true is false, right? And the opposite of false is true. So, yeah. So let's sort of, you good, Josh? Yeah. So let's think about what we exactly mean by this. So here's an example. So P, let's call P the statement Pittsburgh is in Pennsylvania, PA. We'll denote. Then not P is the statement Pittsburgh is not in Pennsylvania. Now, clearly, well, maybe I shouldn't say clearly. So here, P is true, while not P is false. Now, we're using a little bit of English colloquial behavior here. I mean, you could rephrase this sentence. You could say the same fact, writing it differently, right? You could say it's not true that Pittsburgh is in PA, right? You don't necessarily have to write it the same exact way I'm writing it. Do we understand that? Or some books will say it is, I think your book uses this, it is not the case that Pittsburgh is in Pennsylvania. Does that make sense? So another thing it's convenient to do is it's convenient to use truth tables to look at operations. So we want to do that. So what we do is we construct truth tables. So what these do is they illustrate truth values. Of statements. So, for example, the truth table for this particular negation operation would look something like this. So notice I don't care what P is. It can be any statement on the planet. So let's assume we have a statement P. Then, of course, not P looks like this. And then if P is true, we know not P is false. And then if P is false, then we know not P is true. I mean, you could think of the negation operation as like a light switch, on or off, one or the other. That make sense? Anybody have a question, comments, concerns? I can't even go and do a dance because then you guys won't see me. You ever see those pictures on the internet of like these teachers like going, they're gonna like, here's me going into my classroom, just follow like a mask, like a shield on, and like scrubs and all that. All right, any questions, comments? Good, I ain't answering them. You guys gotta be interactive, right? You gotta say, oh Grady, I got questions. What does this mean? I should start giving mental points. Josh gets one and Michelle gets one. They ask questions. What if I started awarding grades by questions asked? And then why, Mackenzie, you don't want to ask questions? That is true. Some people don't like to talk, and that's cool. I don't get mad. It's like I've seen some people complain that I should force you guys on Zoom to show your face. Why would I do that? I don't know what your situation is at home. I don't want to see your dirty room. That ain't fair, right? No offense. If you want to show me, that's fine. But why would I make you do that? It's not fair to you. I don't know what kind of, who knows? Like if I was your age, I was living in a hellhole dirt house with 5 other grimy dudes. I didn't want anybody seeing that. We walk in the front door, there was leaves all over the place. It was disgusting. No one needs to see that. I don't need to see your cats jumping all over you and stuff like that. Right? Anyhow, we're back. Everybody having fun in Zoom land? All right. So we now have, someone's mooring it. Let's see. They're chatting it up. Blast. I like. Jared, there you go. He's out in the hall learning like a true legend. I can't believe we're not just playing theme music the whole damn time we're having class. Sean, you're finally on. Thank God. I felt like I couldn't let you in here. I was going to have to refund you 37 pennies. I like all everybody on the internet. They're like, I want tuition reduced. This is not what the experience I sign on. I'm thinking, man, I've done more work in the past 4 months than I have. Not that I want you to pay me more. I'm just saying. Trying to make this experience the best it is. I'm about to leave this job. No, I'm just kidding. All right, look. So here, now what we want to do is, let's think about these things the way we talk in English. And if we want to combine 2 sentences, there's usually 2 words we use. Or 2 thoughts maybe, or 2 ideas. We use the words and or, right? And these words show up in mathematics all the time. And guess what? They show up in programming all the time too, because, you know, again, if you know anything about how a computer works and the electricity and these gates and all, well, maybe you don't know. I just say these things. I assume so much of you. Anyhow, it's a very important thing. So this is what we want to do now. So next, we need operations to combine statements that play the role of and or. So at this point, it's useful that we start illustrating to you what's a definition. So we're going to say definition. So the correct way to do a mathematical definition is you tell the people what you're going to be doing. So let P and Q be statements. You know, maybe I should use the word, does the book, Mackenzie, do you have the book? You said you were reading it or something. Do they use statements or propositions? Let's use propositions. That way you guys aren't having brain freezes. We'll try to be as consistent as we can. All right, well, now I'm sorry for confusing you. You can have 37 cents back. Ha. So we use the fancy word conjunction. So the conjunction of P and Q is denoted P, and then it's kind of like this caret Q. And it means P and Q. It is true when P and Q are true, and then false otherwise. So it's easier to remember that thinking of a truth table, and we'll do that in a second. So note, this is a definition. And when you start reading examples, and again, I can't do 100 examples. You gotta go use your resources and do this. We're gonna do examples, don't get me wrong, but you have to think about, why would we define it to be this way? Why are we saying it's true when both are true but false otherwise? Well, just make up two sentences that are true and combine them and ask yourself if the whole thing's true, and then do that for each scenario. Right? So let's take two sentences. Ryan is 40, that's true, that's me. Okay? This room is full, that's false. Right? Now let's combine them. Ryan is 40 and this room is full. Is that true or false? Both of them. It doesn't make sense to say that it's a true statement since one of the things is a lie, right? Now if I said Ryan is 40 and this room is not full, well, those are both true statements, so it makes sense to say that the whole sentence is true. I'm not lying to you, correct? So a good way to think about all these definitions is think about lies. Think about when someone can lie to someone, when you just make up sentences. You don't even have to think about math right now. Think sentences. Think English facts and ask yourself, when is it a lie? Hopefully we gather around and make some sense of that. Okay. So here's another definition. And again, think carefully about this. Actually, I don't have to write definition again because we'll put this all under one. These can all be the same definitions, P and Q. Okay, so the disjunction of P and Q is written as P, and then you upside down that little thing, so it's like a V. So this means P or Q. Now there's a technicality here, and how do we deal with the technicality? In English, the word or can mean and or, right? And so we want to consider that scenario. We don't just mean one or the other, we mean one or the other or both. And so how do we make sure we include that subtlety in the English language, really? I don't want to say subtlety, but that sort of the way we use the word. So when is it true? So it is true well, let's maybe rephrase it so it words easier. So it is false is a better way to do it. It is false when both P and Q are. And then it's true otherwise. So the best way to see this is to just do truth tables for both of them. So that's what we're going to do. Now, I have empathy with you because I remember learning this many moons ago and being like, what is happening? Why is this so hard? And so you guys will have many sort of battles with it, and that's okay. So let's draw the truth tables to these creatures. So let's do the one for the conjunction first, the and statement. So we have P and we have Q, and then we want to ask about P and Q. And then over here we have P and we have Q, and then we want to ask about P or Q. So let's go very slowly here. I want you to think about how you can construct these tables, because we want you to be able to construct bigger ones. I mean, we got to build our way up for different things. So if you have a question, now's a good time to ask. Hopefully my notation is clean enough. Okay, so let's go one at a time. We have P and Q, right? P is a statement, or it's a proposition. Sorry, Mackenzie. What do we know about it? It can either be true or false, right? So let's list the options. What are the options? It's true or false. Q has two options. It can be true or false. But if I'm studying them both at the same time, there's more options. Because there's also the scenario where P is true and Q is false. And then lastly, there's a scenario where they're both false. Or excuse me, I wrote that wrong. Let me, I'm sorry, let me be more consistent with how books do it. So put it this way. So if I have two separate statements, and each one of those statements has two options for true and false, that means if I combine them, if I write them in the same statement, the same sentence, then there's four options. They can both be true. Remember, they're generic. They can both be true. One can be true and one can be false, vice versa, and then they both can be false. And if we write it down that way, then what do we know about the and? We know the only time it's true is when they're both true. So all the other truth values are false. And then we can do the same thing for the or statement, the disjunction. And of course, we know that this is the reverse. It's T, 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 F. My encouragement, my way to convince you to learn this is not to memorize it. Memorizing, in my opinion, is the worst thing you can do as a student. I know school doesn't make you think that because they tell you, you got to take these tests, go take. But if you want to take things from you, you want to learn things, don't memorize it. I don't know, wake up in the morning and draw truth tables for 5 minutes. Before you go to bed at night, draw truth tables. When you put your favorite show on Netflix or Hulu and they do some stupid ad for 30 seconds, draw a truth table. Just like if you want to get good at running and playing soccer, you take a ball and run around and kick the damn thing. You want to get good at basketball, you dribble a basketball. Right? You don't just say, let me watch the NBA on TV, I'll be good. That ain't how it works. Just don't work that way. And don't you know, as money hungry as people are, if there was a magic pill you could take to learn this, they would let you do it. Someone would sell that to you. So please don't try to memorize these tables. Try to construct them. Think about them. That's all. I promise you that's the way to learn. So the fancy word for this or, we think about it as meaning one or the other or both. And then there's another sort of thing. We don't use it much in this class, but it's called the exclusive version of or, which means It could be one, but not the other, or vice versa, but not both. Does that make sense? Okay, so if we go back to the very first example that we did, I said we had 3 statements, and I said one was true, the second was true, the third was false, and then downstairs we had something that we didn't consider a proposition. We had like x plus 5 equals 10 because that was not something that was true. But we said if we put an extra condition on it, it might be true or false, right? And so what we want to do is we want to talk about how can we put conditions on statements. Does that make sense? So I keep hitting the wrong mouse pad. It's so funny. There's nothing here. What a time to be alive. Well, I'm saying I'm using my laptop, but I keep hitting this mouse, which is working with this. Okay, so another important way to combine or operate, if you will, propositions is to use what's called a conditional. So I'll put that in quotations because that's not really an actual definition, but I want you to think about it in an English sense, like if this is true, then this is true type thing. So let's make this definition. So if P and Q are propositions, we call P, and then we put this arrow. I like to do it this way. It's like an equal sign with an arrow. So we call this a conditional statement or a conditional proposition. Why did I say propositionals? That doesn't make any sense. Fix that. I had like a English meltdown there. So it means if P, then Q. So for that reason, we call P the hypothesis and Q the conclusion. So if this, then that. So notice I'm saying this is also a proposition, which means by definition it has to have a truth value. So how do we assign truth values here? Well, we look at all the options. P can be true or false. Q can be true or false. Then if we're going to combine them, that means once again we have 4 options. The best way to understand the truth value of a conditional is to ask yourself, When would I lie to somebody? When would I lie? We don't want to lie. If we're going to sort of develop a thing of logic to give rigor to mathematics, we better not have something that has contradictions in the English language. That would be terrible, right? We don't want to lie to people, so we have to ask ourselves, when are we not lying? So what's the truth table look like? Well, let's draw it. So once again, let's think about what options we have here. The options we have are, we have P, we have Q, and then we want to study P implies Q. And of course, P can be true, Q can be true. P can be true, Q can be false, vice versa. And then of course, they can both be false. So let's put some examples in our head to help think about when the truth value of this. Remember, we're making a definition here. It's up to us. We can say that all these are cat. We can say all 4 of these are cat. Would that help us do anything? No. We could say it if we wanted. We could assign all of them to be false or all of them to be true. But it's not useful in that way. Just like it's not useful to say that 4 divided by 6 is 29. We have to make definitions so that they're of use to us and they match our intuition. So let's think of a statement. Let's think of 2 true statements, and let's try to make it seem completely sort of arbitrary. If I say P is the statement, O'Grady is 40, and I say Q is the statement, this room is full. Well, okay, let's do 2 truths first. P is I am 40. Q is La Roche is a college, right? Or university. So if I say, if O'Grady is 40, then La Roche is a university. Did I lie to you at all? No. Does it make sense? Not really, but did I lie to you? No. Make sense? All right, so in that sense, we would say, okay, this should be true. Now let's do another one. O'Grady is 40, this room is full. So if O'Grady is 40, then this room is full. Well, just because I'm 40, that doesn't mean you're going to have a full room here. That one doesn't make the other true, does it? No, so in this sense, we would say that the conditional is false. All right, now let's look at some other scenarios. Let's do a false statement. O'Grady is 37. And then now we need a true statement. La Roche is a university. If O'Grady is 37, then La Roche is a university. Is the fact that I'm 37 always going to make La Roche be a university? No, right? Well, but see, you're overthinking it. Remember, let's say this sentence again. O'Grady is 37, or let's say it in the full English. If O'Grady is 37, then La Roche is a university. Is my conclusion false? No. Doesn't matter what the hypothesis is irrelevant. So the fact that the hypothesis is false is irrelevant to the conclusion. So then we would say it's true. Because I'm not lying to you. The conclusion is true. What if they're both false? O'Grady is 37, this room is full. Did I lie to you? Did I? Did I not fulfill my promise? No, I didn't lie to you because I said, if O'Grady is 37, then this room is full. That statement's not lying. It's a true statement. My promise to you, if then, didn't fall through. So this is the one you're going to have to think about. This is true. So let me be a little more clear. When you're thinking about the truth value of the conditional, you have to ask yourself, does my hypothesis force me to lie about my conclusion? And the only time that's the case is in the second scenario, where I tell you something true and that implies something false. So this might be one you have to spend some time on to make sense, or you can just say, "Oh, memorize it." It's up to you. This is, you can verify that this is the truth table for the conditional. Now, when you read the book, and I'm not going to go through this as all books of this nature do, they will tell you, if I go back a page, I said that it reads if P then Q. There's like 3,000 other ways in English you could say that, right? You could say, for example, Q provided P or something. Like, there's lots of different ways in English, and I'm sure in other languages you can write that sentence. So it doesn't always have to be if then. It's just nice that in math, we often see that. I mean, think about some of the theorems we have talked about in calculus and stuff, or even in algebra class. If this is true, then we must conclude this is true. So, and let me give you one other sort of example that I would encourage you to think about is this. So look at this statement. If you get an A on the final, then you get an A in the course. Well, let's think about the fact you get an A on the final. Say that's true. Then if it is true that you get an A in the course, then I didn't lie to you, did I? I fulfilled my promise. If I tell you you get an A on the final, I'll give you an A for the term, right? So suppose you go and get an A on the final, and then your final grade comes for the course and you've received an A. Did I lie to you? No. What if you got an A on the final, but you didn't get an A in the course? Say you got a B. Would I have lied to you? Yeah, would have, yeah. That's when I didn't fulfill my promise. So that's why the second one is false. And then in the other two scenarios, I would not have lied to you either. Suppose it was true you got an A for the whole course, but you didn't get an A on the final. The conclusion was not a lie. You got an A, right? And similarly, if they're both false. So you got to think about these. Me repeating them and writing it down isn't going to help. You got to really ponder them. One thing I think this book does do is they do have a lot of examples. And so my encouragement to you would be, if there's an example in the book you don't understand, ask me. I'll go over it in class. Okay. Very good. So typically the next thing we talk about is once we have an if-then statement, then we ask about what are different ways to sort of study that same statement. So definition. Given P implies Q, or if P then Q, we call Q implies P the converse, not Q implies not P the contrapositive, and not P implies not Q the inverse. So one of the things you should practice doing is you should write truth tables out for these. It's a good exercise. So let me remind you of that. So a cool fact that you'll notice is that the contrapositive and the conditional have the same truth values, which is great because what that means is that they're logically the same thing. So what's cool about that is that allows you oftentimes to study one thing by studying something else that's equivalent. We'll use that a ton this semester. So I think I asked you to do something like this for homework. Let's do an example. So if it rains tomorrow, then I'll sleep until noon. So what would be the converse? Well, if I go back, it's useful to remind yourself what's P and what's Q. So the converse is the conclusion implies the hypothesis. So the converse would be if I sleep till noon, then it rains. Then the contrapositive would mean if I don't sleep till noon, then it doesn't rain. And then, of course, what does the inverse mean? Well, the inverse is not. So that would be if it doesn't rain, then I won't sleep till noon. So again, these are some things you're not going to learn this in like 5 or 10 minutes. If you really want to try to get an appreciation for this and why it's useful, and try to actually gain something from it, it's going to take some effort on your part, but that's okay. I mean, that's part of the fun. And by the way, computers very much operate on the same thing. I mean, as many of you know, computers communicate, they use bits, zeros and ones, and that's just the same thing structurally as an F and a T. And so everything we're doing here is really how a computer really works. It's these logic gates, and you know, some of you might know this, some of you will get to learn all that. And trust me when I say this, everything that seems overwhelming right now about learning this, at some point, if you give it effort, it will be gone. This stuff is not, it's not terribly difficult. But again, everything that's new to us is difficult, right? No one expects us to learn this stuff right away. It's helpful if you've seen it before, which most of you haven't. Fortunately, I did many times, and I've taught it many times, so it's useful. All right, the last sort of conditional that we're going to talk about is extremely important is the following. So we call the proposition P, and I'm going to use it. It looks similar, but it has a double arrow. We call this the biconditional of P and Q. Sometimes we read this as it's often read as P if and only if Q. So it's equivalent to P implies Q and Q implies P. So what does this mean? So we need another definition. So we say two propositions are equivalent when they have the same truth values. So one of the best ways to see that is to draw some truth tables. So probably the last thing we should do then is we should draw a truth table for the biconditional. Yeah. Oh, sure, yeah. Sorry about that. Sorry. Got it? No, you're good. All right, so if we go to the next page, what we want to do is we want to draw this truth table, and we're going to start it off very much like we did the last ones. This is how I like to do it. Kind of everybody does theirs a little differently. This is just sort of how I do mine. So we have our two propositions, P, Q, and once again, we have the scenario they're both true, the scenarios where one's true and the other's false, and then, of course, the scenario where they're both false. And so what is P if and only if Q? Well, it's true when they're both true, false when they're not both true, and then it's also true when they're both false. So you should do the following. This is good practice, I would do. So you should use truth tables to verify that P, if and only if Q is equivalent to P implies Q. Now let's look, how would we combine the and statement of two propositions? Well, the logical way of doing that would be like this. So there's an inherent order of operations on these things, much like when you do arithmetic, there's an order of operations. You sort of work from the outside in, or excuse me, inside out. So in order so that we don't have these sort of ambiguities, like what do I do first, we use grouping symbols. So grouping symbols in propositional logic mean the same thing they mean when you're doing algebraic manipulations or arithmetic. If you look at this last sentence, the parentheses say, do what's in the parentheses first, figure the truth value out for that, then do the and, just like you would do if you were doing order of operations in 6th grade. Does that make sense? So how do we prevent there from being ambiguities? We use parentheses. We use grouping operations. So what do I mean by ambiguities? What I mean is, and this is the last thing I'll say, I promise. So use grouping symbols to avoid confusion. So the last thing I'll say about it is for example, does, say, P and Q or R mean, does it mean P and Q or R, or P and Q or R? Do you understand what I'm saying here? This first thing I wrote, this guy right here, I'll highlight it in red. This is confusing. I mean, even imagine an English sentence that was structured that way. It doesn't make sense. You need to have better structure to your sentence for it to be clear. So this might not come as an issue to you right now, but it will. All right, so what I need you guys to do is start working on this homework. I need you to ask questions. I need you guys to bring questions Monday to class, and have a great weekend. Yes, Michelle, you have a question? Yeah, I did.
Oh, okay.
Yeah. So I mean, in the sense that I'm not asking you who's here, I'm looking who's on the internet, and I'm looking who's here in person. And then now that I mean, I know all of you, right? Really, I only met Dimitri. He's new to me. That's it. The rest of you I know. All right, guys, have a good one. Thank you very much. I will.